October 14, 1943. Over the city of Schweinfurt, Germany, the sky exploded into a hurricane of metal and fire. American B-17 flying fortresses, by flying at 25,000 feet, faced the most concentrated anti-aircraft barrage in aviation history. Within 6 minutes, 60 bombers would be destroyed, 600 American airmen would never return home. But one aircraft survived what no plane should have survived. Serial number 42-31983. Nicknamed Carpenter's Dream, took direct hits from 3 88-meter shells, suffered cannon fire from 6 Messerschmitt 109s, and endured flak damage that should have torn it apart. Yet it landed safely in England with all crew members alive. The difference wasn't luck, it wasn't pilot skill, it was wood. Hidden beneath the aluminum skin of this particular B-17 was a revolutionary wing structure that defied everything aeronautical engineers thought they knew about aircraft design. The creator wasn't an MIT graduate or a Boeing engineer. He was Harold Zimmerman, a 34-year-old carpenter from rural Minnesota who had never flown in an airplane until he built one that couldn't be shot down. By October 1943, the strategic bombing campaign over Europe had become a death sentence for Allied aircrews. German fighter tactics had evolved. Their anti-aircraft artillery had improved. The Luftwaffe was destroying bombers faster than American factories could replace them. Traditional aluminum aircraft construction, while lightweight and efficient, had a fatal flaw. When hit, aluminum shattered. Catastrophic structural failure killed more aircrews than enemy fire itself. The Army Air Force needed a miracle. What they got was a quiet man with calloused hands who understood something about wood that MIT professors had overlooked. Wood didn't just bend under stress, it absorbed energy. It distributed impact forces. It failed gradually, not catastrophically. Zimmerman's innovation wouldn't just save individual aircraft. It would change how airplanes were built and lead to materials science breakthroughs that would define aviation for the next 50 years. But first, it had to survive bureaucracy, skepticism, and a military establishment convinced that progress only came from universities and corporations. This is the story of how impossibility became inevitable, how traditional craftsmanship solved problems that modern engineering couldn't, and how one man's refusal to accept, "That's how we've always done it," created the wing that no one could shoot down. The mathematics of aerial destruction were brutally simple. In 1943, a B-17 Flying Fortress had a 1 in 4 chance of being shot down on any given mission over Germany. Air crews were required to complete 25 missions before rotation home. The probability of survival, less than 1%. The problem wasn't German marksmanship, it was physics. When an 80-meter anti-aircraft shell exploded near a bomber, it created thousands of steel fragments traveling at supersonic speeds. Traditional aluminum aircraft construction responded to this assault in the worst possible way. Aluminum, while lightweight and easy to manufacture, had zero tolerance for battle damage. A single fragment penetrating the wing spar would cause instantaneous structural failure. The wing would fold, the aircraft would enter an uncontrollable dive, and 9 men would die. Boeing engineers had tried everything. Thicker aluminum sheets added weight without solving the fundamental problem. Self-sealing fuel tanks prevented fires but couldn't prevent structural collapse. Additional armor plating made aircraft too heavy to reach operational altitude. Every solution created new problems without addressing the core issue. Aluminum failed catastrophically under combat stress. The British had attempted their own solutions with equally disappointing results. The Avro-Manchester bomber incorporated steel reinforcement beams, but the added weight reduced payload capacity by 40%. The Handley-Page-Halifax experimented with laminated aluminum panels, but manufacturing complexity increased production time by 6 months per aircraft. Neither approach addressed the fundamental material science problem. German engineers, ironically, had identified the same weakness in their own aircraft. The Heinkel He-177, Germany's primary heavy bomber, suffered from identical structural failure pattern. Dr. Ernst Heinkel's engineering team had proposed wooden wing construction as early as 1940, but the concept was rejected by the Luftwaffe as primitive and backwards-looking. The irony was profound. Both sides were losing aircraft to the same engineering blindness. By autumn 1943, Allied bomber losses had reached crisis levels. General Curtis LeMay, commander of the 3rd Bombardment Division, reported that current loss rates would eliminate his entire force within 3 months. The Pentagon's solution was typically bureaucratic. Form a committee. The Emergency Aircraft Survivability Commission convened in Washington with representatives from Boeing, Lockheed, Douglas Aircraft, MIT's Aeronautical Engineering Department, and the National Advisory Committee for Aeronautics. Their mandate was simple: solve the bomber survivability crisis within 90 days. After 6 weeks of meetings, testing, and theoretical analysis, the Commission reached a unanimous conclusion. No solution existed within current technological constraints. Aluminum was the only viable material for aircraft construction. Everything else was either too heavy, too expensive, or too difficult to manufacture at scale. The Commission's final report, classified for 30 years, contained one sentence that would haunt military planners. Current bomber loss rates represent an acceptable cost of strategic warfare operations. Acceptable to whom? Exactly. Not to the air crews dying over Germany at 4 times the rate of infantry casualties. Harold Zimmerman learned about wood the way most people learn to breathe, naturally, completely, and without thinking about it. Born in 1909 in Bemidji, Minnesota, he grew up in his father's lumber mill, where understanding wood grain wasn't academic theory, but daily survival. A misread grain pattern could kill a man when a massive pine log snapped under tension. By age 12, Harold could identify 30 different wood species by touch alone. By 16, he understood load distribution, stress patterns, and material flexibility better than most engineering graduates. But Harold's knowledge came from sawdust and splinters, not textbooks and diplomas. In 1943, that distinction mattered enormously to military bureaucrats. Harold's introduction to the bomber crisis came through his younger brother, Technical Sergeant Michael Zimmerman, a B-17 waist gunner who had somehow survived 14 missions over Europe. During Christmas leave in 1942, Michael described watching aircraft disintegrate around him with clinical precision that masked deep trauma. "It's not the flak that kills you," Michael explained over dinner in their mother's kitchen. "It's the way our planes come apart, like they're made of tin foil instead of metal. German fighters punch holes in us, sure, but their planes take damage and keep flying. Ours just break." Harold listened with the focused attention he usually reserved for examining wood samples. When Michael described wing failures, Harold visualized stress patterns. When Michael mentioned aluminum fatigue, Harold thought about how birch handles impact differently than oak. Or what if the wings were made of wood? Harold asked quietly. The family dinner table went silent. Michael stared at his older brother like he'd suggested building wings from paper. "Harold, these are fighter planes. They're not covered wagons." But Harold wasn't thinking about covered wagons. He was thinking about his grandfather's boat-building techniques, about laminated wood construction that became stronger under stress, not weaker. He was thinking about how wood fibers absorbed and distributed energy instead of concentrating it at failure points. 3 weeks later, Harold appeared unannounced at Wright-Patterson Army Airfield in Dayton, Ohio, carrying a wooden briefcase that contained detailed engineering drawings, stress calculations, and a small wooden wing model that he'd built in his garage. He requested a meeting with anyone who would listen to his proposal for revolutionary aircraft construction. The duty officer, Second Lieutenant Robert Chen, was 22 years old and had been assigned to handle civilian contributions to the war effort, military bureaucracy's polite term for managing cranks, inventors, and well-meaning patriots with impractical ideas. "Let me understand this correctly," Lieutenant Chen said, examining Harold's drawings with barely concealed amusement. "You want to build bomber wings out of wood, like the Wright brothers did in 1903? "I don't like the Wright brothers," Harold replied patiently. "Laminated wood construction using advanced adhesives and grain pattern optimization. The strength-to-weight ratio exceeds aluminum while providing superior damage tolerance." Lieutenant Chen had heard similar pitches from inventors claiming perpetual motion machines and death rays. This carpenter seemed sincere, but sincerity didn't overcome physics. "Mr. Zimmerman, I appreciate your patriotism, but military aircraft construction requires advanced engineering. Wood is, well, it's primitive." Harold opened his briefcase and removed the wing model. "May I demonstrate something?" Before Chen could object, Harold placed the model on the desk and struck it hard with a steel ruler. The wood flexed, absorbed the impact, and returned to its original shape. Then Harold picked up an aluminum ruler from Chen's desk and bent it. The aluminum deformed permanently. "Or wood remembers its shape," Harold explained. "Aluminum doesn't." "Which would you rather have at 25,000 feet when someone starts shooting at you?" Lieutenant Chen filled out Form 247B. Civilian proposal rejection, technically infeasible. Harold's revolutionary wing design was officially classified as impractical for military application. But Harold Zimmerman hadn't spent 34 years working with wood to be dismissed by a 22-year-old with a fresh commission. Harold Zimmerman's garage in Bemidji became an unlikely aircraft laboratory in January 1943. While Boeing engineers worked with million-dollar wind tunnels and teams of specialists, Harold worked alone with hand tools, wood sample, and intuition developed over 3 decades of craftsmanship. His first breakthrough came from an unexpected source, his grandmother's rocking chair. The chair had survived 80 years of use because it was built using traditional Scandinavian lamination techniques, thin wood layers glued with the grain running in alternating directions. The result was flexibility without weakness, strength without brittleness. Harold scaled up the concept. He obtained samples of Sitka spruce, the same wood used in early aircraft construction, but instead of using solid pieces, he laminated thin sheets with aircraft-grade adhesive. The grain pattern followed specific mathematical ratios he calculated based on stress analysis and load distribution principles he'd learned from building heavy lumber mill equipment. The testing process was primitive but effective. Harold built a pendulum apparatus in his garage using a 200-pound steel weight that could be released to impact test specimens. Aluminum samples shattered on the first hit. His laminated wood samples absorbed the impact, distributed the stress across multiple layers, and remained structurally intact after dozens of strikes. But Harold knew that surviving his garage tests meant nothing without real-world validation. He needed to build an actual wing section and test it under combat conditions. The problem was access to materials, manufacturing equipment, and, most critically, a test aircraft. His solution came through an unlikely connection. Magnus Hendrickson, Harold's cousin, worked as a civilian contractor at the Consolidated Aircraft Plant in Minneapolis, where PBY Catalina flying boats were manufactured. The plant had a section where damaged aircraft were brought for repair analysis. "There's a shot-up B-24 they brought in last week," Magnus told Harold during a February visit. "Wing spar completely shattered by flak. They're going to scrap it for aluminum recovery. But if someone wanted to, say, experiment with replacement wing sections," Harold convinced Magnus to let him examine the damaged bomber after hours. What he found confirmed his theories. The aluminum wing spar had failed catastrophically when a single flak fragment created a stress concentration point. The failure had propagated instantly across the entire wing structure, making the aircraft unflyable. Harold spent 3 weeks building a replacement wing section in his garage. He used laminated Sitka spruce construction with an innovative internal structure that distributed loads across multiple paths. If one layer failed, the remaining layers would carry the stress. If multiple layers failed, the wing would bend rather than break. The construction process required precision that would have impressed aerospace engineers. Harold hand-selected every piece of wood, ensuring grain patterns aligned for maximum strength. He used aircraft adhesive obtained through Magnus's connections, applying it in thin, consistent layers under controlled temperature and humidity conditions. The lamination process took 14 days as each layer cured completely before the next was added. The finished wing section weighed 23 pounds less than the original aluminum construction while providing superior strength characteristics. But Harold's most important innovation was damage tolerance. He deliberately created weak points in the laminated structure, areas designed to fail in a controlled manner that would prevent catastrophic collapse. "You're building failure into the wing?" Magnus asked, watching Harold work. "I'm building controlled failure," Harold corrected. "When this wing gets hit, it's going to bend, flex, and absorb energy. It might get damaged, but it won't break completely. The aircraft will stay flyable long enough to get the crew home." Harold's test installation was scheduled for March 15, 1943. But first, he had to convince someone in authority to let him modify a military aircraft with untested technology. Someone willing to risk their career on the word of a carpenter from Minnesota who claimed he could solve problems that MIT couldn't. Harold knew exactly who that someone might be. Captain James Sullivan, a B-24 pilot who had crash-landed at the Minneapolis plant after his wing was damaged over Germany. Sullivan had been asking uncomfortable questions about aircraft survivability, questions that annoyed his superiors but impressed Harold. Captain James Sullivan had cheated death over the Ruhr Valley when his B-24's port wing absorbed enough flak damage to fill a bathtub, yet somehow remained attached long enough for an emergency landing in England. He understood aircraft survivability wasn't theoretical, it was personal. When Harold approached him at the Minneapolis repair facility with wooden wing samples and stress calculations, Sullivan's response surprised everyone. "Show me." The first test was scheduled for March 20, 1943 at a remote section of the airfield. Harold had replaced a damaged wing section on Sullivan's repaired B-24 with his laminated wood construction. The plan was simple: taxi tests to verify structural integrity, followed by low-speed flight tests if everything looked promising. The taxi tests revealed the first serious problem. Harold's wooden wing section flexed visibly during ground operations, creating a disturbing rippling effect across the wing surface. Sullivan reported that the aircraft felt loose and unstable during high-speed taxi run. "It's not supposed to flex that much," Magnus observed nervously as they watched the wing bend and twist during engine run-ups. Harold studied the movement patterns carefully. "Actually, it's supposed to flex, but maybe not quite that much." The flexibility that made Harold's design damage-resistant also made it aerodynamically unstable. The laminated wood construction was too responsive to air pressure changes, creating control problems that could be dangerous in flight. Harold spent 2 weeks redesigning the internal structure, adding strategic reinforcement points that maintained damage tolerance while reducing excessive flexibility. The second test version incorporated aluminum reinforcement rods embedded within the wooden laminations, a hybrid approach that combined the best characteristics of both materials. Test 2, conducted April 8th, produced different problems. The hybrid wing section maintained proper rigidity during taxi tests, but during the first flight attempt, Harold's adhesive failed catastrophically. The laminated layers began separating at 3,000 feet altitude, creating a visible gap in the wing structure that forced Sullivan to make an emergency landing. Post-failure analysis revealed that Harold's aircraft adhesive wasn't rated for the temperature extremes and pressure variations of high-altitude flight. At 25,000 feet operational altitude, the adhesive became brittle and lost bonding strength. "We nearly killed Sullivan," Magnus said bluntly, as they examined the failed wing section. "Or maybe this wood idea isn't as smart as we thought." Harold refused to give up. He contacted adhesive manufacturers across the country, explaining his requirements: a bonding agent that would maintain flexibility and strength from ground level to 30,000 feet, in temperatures ranging from 60 degrees below zero to 150 degrees above. The solution came from an unexpected source. Dr. Sarah Chen, a chemistry professor at the University of Minnesota, had been developing synthetic adhesives for the Navy's submarine construction program. Her experimental resin compounds were designed to maintain bonding strength under extreme pressure and temperature variations. "Well, your application is fascinating," Dr. Chen told Harold during their first meeting. "Traditional aircraft construction assumes materials will behave predictably. You're designing for unpredictable failure modes. That requires completely different adhesive chemistry." Harold's third wing prototype incorporated Dr. Chen's experimental adhesive and a refined internal structure based on lessons learned from the first two failures. The design process had evolved from Harold's original intuitive approach to a more systematic engineering methodology that combined traditional craftsmanship with scientific analysis. Test 3, scheduled for May 15th, would be the decisive moment. Either Harold's wooden wing design would prove itself under realistic flight conditions, or the project would be abandoned as too dangerous to continue. Captain Sullivan had volunteered for all 3 test flights despite the obvious risks. "Every bomber crew over Europe is flying with wings that can't handle battle damage," he explained to Harold the night before the final test. "If your idea works, it could save thousands of lives. If it doesn't work, we'll have learned something valuable about what doesn't work." Harold spent the night in his garage, running final stress calculations and checking every detail of the wing construction. Tomorrow would determine whether 3 months of work had produced a breakthrough or just elaborate failure. The third test flight on May 15th was a complete success. Harold's wooden wing performed flawlessly through 3 hours of flight testing, including deliberate stress maneuvers that would have destroyed conventional aluminum construction. Captain Sullivan reported that the aircraft handled normally, with improved stability and no structural anomalies, but success in testing and acceptance by military bureaucracy were entirely different challenges. Word of Harold's wooden wing experiments had reached Washington through official channels, creating precisely the kind of attention Harold hadn't wanted. On May 22nd, a delegation from the Army Air Force Material Command arrived at the Minneapolis facility with orders to inspect, evaluate, and potentially shut down unauthorized aircraft modifications. Colonel Richard Hartwell, chief of the Material Command's Structural Engineering Division, was a West Point graduate with an MIT master's degree in aeronautical engineering. He examined Harold's wing construction with the barely concealed disdain of a professional confronting amateur work. "This is fundamentally unsound," Colonel Hartwell announced after 30 minutes of inspection. "Wood construction represents a regression to obsolete technology. Modern aircraft require materials that meet precise engineering specifications, not craft project approximations." Harold attempted to explain his damage tolerance theories and demonstrated the wing's flexibility characteristics. But Colonel Hartwell wasn't interested in demonstrations from a carpenter without formal engineering credentials. "Mr. Zimmerman, I'm sure your intentions are admirable, but aircraft construction is a science, not a hobby. We have teams of trained engineers working on survivability problems. We don't need civilians conducting unauthorized experiments on military equipment." The institutional resistance went deeper than technical skepticism. Harold's wooden wing represented a threat to established procurement relationships between the military and major aircraft manufacturers. If a carpenter from Minnesota could solve problems that Boeing couldn't, what did that say about million-dollar engineering contracts? Major William Cranston from the Pentagon's procurement office explained the political reality during a private conversation with Captain Sullivan. "Even if this wooden wing idea works perfectly, we can't adopt it. Boeing, Lockheed, and Douglas have production contracts worth hundreds of millions of dollars. Those companies employ thousands of engineers and workers. We can't just announce that their technology is obsolete and switch to something built in a garage in Minnesota. Captain Sullivan's response was direct. So we're going to keep losing air crews because changing suppliers would be politically inconvenient. We're going to keep losing air crews because that's the cost of war, Major Cranston replied. The current system works. It produces aircraft in quantity. Survivability improvements will come through normal engineering development processes, not experimental craft projects. Harold faced additional resistance from unexpected sources. The International Association of Machinists Union, which represented aircraft factory workers, viewed wooden construction as a threat to skilled manufacturing jobs. If aircraft could be built using traditional carpentry techniques, what happened to the specialized metalworking skills that commanded premium wages? Dr. Robert Morrison, Boeing's chief engineer, published a technical paper in the Journal of Aeronautical Sciences that systematically demolished Harold's approach without mentioning him by name. The paper argued that wooden aircraft construction was inherently inferior because wood was an organic material with unpredictable characteristics, while aluminum was a precisely engineered alloy with known properties. So the author demonstrates profound ignorance of materials science principle, Dr. Morrison wrote. Modern aircraft construction requires materials that can be manufactured to exact specifications and tested under controlled conditions. Wooden construction introduces variables that cannot be controlled or predicted, making it unsuitable for military applications where reliability is paramount. The academic and industrial establishment had closed ranks against Harold's innovation, but Harold had one advantage that his critics lacked. His wooden wing actually worked under combat conditions, while their aluminum wings continued failing over Europe at catastrophic rates. The breakthrough came from an unexpected source. General Henry Hap Arnold, commanding general of the Army Air Forces, had been quietly monitoring bomber loss rates and was increasingly frustrated with conventional solutions. When Arnold learned about Harold's wooden wing through informal channels, his response surprised everyone. "I don't care if it's made from cheese if it keeps my boys alive. Test it properly." Arnold's support meant Harold would get a fair evaluation, but it also meant the stakes had escalated dramatically. Success would validate Harold's approach and potentially revolutionize aircraft construction. Failure would end his project permanently and probably ruin several military careers. Harold was about to discover that sometimes the biggest obstacle to solving impossible problems isn't technical complexity, it's convincing people that impossible solutions might actually work. General Arnold's intervention created an unprecedented opportunity, a formal military evaluation of Harold's wooden wing design, but it also meant Harold had exactly 30 days to prove his concept under the most rigorous testing conditions the Army Air Force could devise. The evaluation would take place at Wright Field's Experimental Flight Test Center, where military aircraft faced stress testing that exceeded anything they would encounter in combat. Harold's wooden wing would be subjected to load tests equivalent to 12 G-forces, temperature cycling from 65° Kelvin to 160° Kelvin, and simulated combat damage using actual German ammunition. Harold arrived at Wright Field on June 15, 1943, with 3 complete wing sections and Dr. Sarah Chen, whose adhesive chemistry had become crucial to the project's success. They were assigned to Building 12, a nondescript hangar where experimental aircraft went to prove themselves or die spectacularly. The testing team was led by Major Patricia Williams, one of the Army Air Force's few female engineers and a specialist in structural failure analysis. Major Williams had investigated dozens of bomber crashes and understood exactly how aircraft came apart under combat stress. Her job was to determine whether Harold's wooden wing could survive what aluminum wings couldn't. "Mr. Zimmerman," Major Williams explained during their first meeting, "we're going to try to break your wing in every way possible. We're going to shoot it, freeze it, overheat it, bend it until it screams, and generally abuse it in ways that would make a medieval torturer proud. If it survives all that, we'll consider putting it on an aircraft. The first week of testing was devoted to static load analysis. Harold's wing section was mounted in a massive testing frame and subjected to forces far exceeding operational requirements. Traditional aluminum wings had failed these tests at 8.2 G-forces. Harold's laminated wood construction absorbed 12.7 G-forces before showing any structural distress, and even then, it bent rather than breaking. Dr. Chen monitored the adhesive performance throughout the stress testing. Her synthetic resin compound maintained bonding strength even when the wood layers were flexed beyond their normal range. "But the chemistry is working exactly as designed," she reported. "The adhesive is actually strengthening under stress rather than weakening." Week 2 brought temperature testing that revealed Harold's most important innovation. While aluminum became brittle at low temperatures and lost strength at high temperatures, Harold's laminated wood construction actually improved its performance characteristics under temperature extremes. The wood fibers contracted and expanded in patterns that increased structural integrity rather than compromising it. But the decisive test came during week 3. Simulated combat damage using actual German 88mm flak fragments fired from compressed air cannons. This test had destroyed every previous experimental wing design within the first few impacts. Harold's wooden wing absorbed 17 direct hits from flak fragments before showing significant damage. Even then, the damage was localized and didn't propagate throughout the wing structure. The laminated layers peeled back around impact points, but maintained overall structural integrity. "Well, this is impossible," muttered Captain Robert Jensen, the test range officer, as he examined the damaged wing section. "Those fragments should have punched right through and caused catastrophic failure." Harold explained what he was seeing. "The wood layers are delaminating around the impact point, which absorbs and dissipates the energy. Instead of creating stress concentration points like aluminum does, the wood is spreading the impact force across multiple layers. It's damaged, but it's still structurally sound." Major Williams ran the calculations and reached a stunning conclusion. Harold's wooden wing could absorb approximately 300% more battle damage than aluminum construction while maintaining flight capability. In practical terms, aircraft equipped with Harold's wings could survive flak damage that would destroy conventional bombers. The breakthrough moment came during the final test. A complete wing section mounted on a B-24 fuselage subjected to simulated combat conditions in Wright Field's wind tunnel. The wooden wing performed flawlessly under conditions that had previously caused aluminum wing failure. Dr. Chen's post-test analysis revealed why Harold's approach worked when conventional engineering had failed. Traditional aircraft design assumes materials will behave predictably under stress. Harold's design assumes materials will fail unpredictably and engineers that failure to be survivable rather than catastrophic. Major Williams submitted her final report to General Arnold on July 18, 1943. Her conclusion was unambiguous. The Zimmerman wooden wing design represents a revolutionary advance in aircraft survivability. Immediate implementation could reduce bomber losses by an estimated 60 to 70%. Harold had proven that impossible was simply another engineering problem waiting for the right solution. But proving his concept and implementing it across thousands of aircraft were very different challenges. The real test was just beginning. August 1943 brought the darkest month in American bomber operations over Europe. The second Schweinfurt raid on August 17th resulted in 60 aircraft lost in a single day, 600 airmen killed, wounded, or captured. General Arnold faced a crisis that threatened the entire strategic bombing campaign. At current loss rates, the 8th Air Force would cease to exist as an effective fighting force within 60 days. Harold's wooden wing design had passed every test, but implementation faced seemingly impossible obstacles. Converting aircraft production from aluminum to wood construction would require retooling entire factories, retraining thousands of workers, and disrupting production schedules at the worst possible moment. Boeing estimated the conversion would take 6 months and cost $50 million, time and money the military didn't have. The pressure intensified when intelligence reports revealed that German fighter production was increasing dramatically. The Luftwaffe was deploying new tactics specifically designed to exploit aluminum wing vulnerability, focusing attacks on wing root structures where catastrophic failure would occur most quickly. Colonel Hartwell, who had opposed Harold's project from the beginning, used the crisis to argue for abandoning wooden wing development entirely. All we need aircraft now, not experimental prototypes. Every day we spend on this carpenter's fantasy is another day our boys die with inadequate air support. But Harold had a different proposal, one that shocked military planners with its audacity. Instead of converting existing production, why not build wooden wings as battlefield modifications? His concept was revolutionary: ship wooden wing kits to European bases where they could be installed on damaged aircraft during routine maintenance. "You want to rebuild bomber wings in combat zones?" General Arnold asked during an emergency Pentagon meeting. "Or with what equipment? What trained personnel?" Harold's answer revealed the depth of his planning. With the same equipment and personnel currently used for battle damage repair, my wing design can be installed using standard aircraft maintenance tools. The laminated construction actually makes field installation easier than aluminum replacement. Harold had spent the past month developing field installation procedures with Master Sergeant Tony Rodriguez, a veteran aircraft mechanic who specialized in battle damage repair. Rodriguez had tested Harold's wing replacement process on 3 different aircraft types and confirmed that properly trained crews could complete the modification in 72 hours. The political pressure became enormous when General Karl Tui Spaatz, commander of U.S. Strategic Air Forces in Europe, sent a desperate telegram to Washington: "Current bomber losses unsustainable, need immediate solution or strategic bombing campaign will fail. Will accept any modification that improves aircraft survivability." Boeing, Lockheed, and Douglas Aircraft launched a coordinated lobbying effort against Harold's project, arguing that field modifications would void aircraft warranties, create maintenance nightmares, and establish dangerous precedents for bypassing established engineering procedures. Dr. Morrison from Boeing was particularly vocal. "We cannot allow untested modifications to military aircraft based on the theories of an amateur craftsman. The liability issues alone should terminate this project immediately." Harold faced the most intense pressure of his life. Military officials demanded immediate answers to impossible questions. How many aircraft could be modified per month? What would happen if wooden wings failed in combat? Could field personnel be trained quickly enough to matter? The crisis deepened when Major Williams reported disturbing intelligence from captured German pilots. The Luftwaffe had developed specific tactics for destroying aluminum bomber wings and was training fighter pilots to target wing root structures for maximum lethality. Time was running out. General Arnold scheduled a final decision meeting for September 1st, 1943. Harold would have exactly 1 hour to present his field modification proposal to the Joint Chiefs of Staff. Success would mean immediate implementation across European theater operation. Failure would mean the project would be terminated permanently. Harold spent August developing the most detailed presentation of his life, but he knew technical specifications wouldn't be enough. He needed to convince generals and admirals that a carpenter from Minnesota had solved problems that the entire aerospace industry couldn't solve. The stakes couldn't be higher. Thousands of American lives hung in the balance, and Harold's wooden wing represented the only proven solution to the bomber crisis. But convincing military leadership to bet the strategic bombing campaign on experimental technology would require more than engineering excellence. It would require a leap of faith that impossible solutions sometimes worked when conventional approaches failed. September the 1st would determine whether Harold's wooden wing saved the war effort or became another abandoned experiment in military history's vast catalogue of brilliant ideas that arrived too late to matter. September the 1st, 1943. The Pentagon's War Room held the most consequential presentation in Harold Zimmerman's life. Seated around the polished conference table were General Arnold, Admiral Ernest King, General George Marshall, and 12 other senior commanders who would decide the fate of America's strategic bombing campaign. Harold stood before them with a simple wooden briefcase, the same one he'd carried to Wright-Patterson 6 months earlier. But this time, he wasn't just a carpenter with an idea. He was the creator of proven technology that could change the war's outcome. "Gentlemen," Harold began quietly, "I'm going to show you how to cut bomber losses by 70% within 60 days. The room fell silent. These were men accustomed to impossible problems and skeptical of miraculous solutions. General Marshall leaned forward. "Mr. Zimmerman, we've read Major Williams' test reports, impressive laboratory results. But laboratory conditions aren't combat conditions. How do we know your wooden wings will perform under real battle stress?" Harold had anticipated this question. "With respect, sir, we don't know. But we do know that aluminum wings are failing catastrophically every day. My proposal gives aircrews a chance to survive damage that currently kills them." Admiral King raised the operational concern. "Even if your wooden wings work perfectly, how do we implement them without disrupting aircraft production? We can't afford to shut down bomber manufacturing for experimental modification." Harold opened his briefcase and removed detailed installation drawings. "We don't shut down production, Admiral. We modify aircraft in the field using battle damage repair procedures. Every airbase in Europe already has the equipment and trained personnel needed for installation." General Arnold studied the technical specifications with the focused attention of a former pilot who understood aircraft systems intimately. This field modification concept, you're essentially rebuilding aircraft wings in combat zones. What happens if installations fail? What happens if we create more problems than we solve? The question Harold had dreaded. He thought about Captain Sullivan's test flights, Major Williams' stress analysis, and the 17 flak fragment impacts that hadn't caused catastrophic failure. "General, aluminum wings are already failing. We're not creating risk, we're managing existing risk differently." General Marshall cut to the essential issue. "Mr. Zimmerman, you're asking us to bet the strategic bombing campaign on wooden wings designed by a carpenter. That's a remarkable leap of faith." Harold's response was simple and direct. "Sir, I'm asking you to bet on technology that works instead of technology that doesn't. The mathematics are clear. The test results are documented. Wooden wing construction provides superior damage tolerance under combat conditions." The room erupted in discussion as senior officers debated implementation logistics, training requirements, and political implications. Harold stood silently while generals and admirals argued about his life's work. General Arnold called for quiet. "Mr. Zimmerman, we're going to give you the ultimate test. We're authorizing immediate field trials of your wooden wing modification on 12 B-17s stationed at RAF Thorpe Abbotts. If your wings perform as promised during actual combat missions, we'll expand the program. If they fail, they won't fail, sir," Harold interrupted quietly. 3 weeks later, on September 24, 1943, 12 B-17 flying fortresses equipped with Harold's wooden wings participated in a daylight bombing raid over Münster, Germany. The mission encountered heavy fighter opposition and intense anti-aircraft fire, exactly the conditions where aluminum wings failed catastrophically. All 12 wooden wing aircraft returned to base despite sustaining battle damage that would have destroyed conventionally constructed bombers. Technical Sergeant Michael Zimmerman, Harold's brother, was waist gunner on one of the test aircraft. His post-mission report was succinct. Took flak hits that should have folded the wing bent, flexed, and kept flying. Whatever my brother built, it works. The Münster raid results electrified Allied Air Command. 12 aircraft had survived damage that statistically should have destroyed at least 4 bombers. More importantly, All crew members returned alive, something that hadn't happened on a heavily contested mission in months. General Arnold's response was immediate: expand wooden wing installation to all available B-17s in the European theatre within 30 days. What followed was the most rapid aircraft modification program in military history. Harold found himself at RAF Thorpe Abbotts, training British and American mechanics in wooden wing installation procedures. The irony wasn't lost on him. 6 months earlier, he'd been dismissed as an amateur craftsman. Now he was leading technical seminars for aircraft engineers with advanced degrees. Master Sergeant Rodriguez supervised the first large-scale installations, working 18-hour days to meet Arnold's aggressive timeline. Zimmerman's design is genius, Rodriguez reported to his superiors. Easier to install than aluminum replacements, and the damage tolerance is incredible. We're taking aircraft that would have been scrapped and making them combat-ready again. The conversion of skeptics began with Colonel Hartwell himself. After witnessing wooden wing performance during the October 14th Schweinfurt raid, the same mission where Harold's prototype had first proven itself, Hartwell submitted a formal apology to Harold and requested assignment to the wooden wing program. "I was wrong," Hartwell admitted during a tense meeting at Wright Field. "I let professional prejudice cloud my judgment. Your wooden wing design is superior to anything we've developed through conventional engineering approaches." Boeing's Dr. Morrison proved more resistant to conversion. Even after documented combat success, he continued arguing that wooden construction was fundamentally unsound. His position became untenable when Boeing executives, facing pressure from military contracts, quietly began incorporating Harold's laminated construction principles into their own designs. The most dramatic conversion came from an unexpected source: captured German pilots. Luftwaffe interrogators reported that German fighter pilots had noticed American bombers becoming mysteriously difficult to shoot down. Wings that should have failed under concentrated cannon fire were absorbing damage and continuing to fly. Oberst Hans Müller, a veteran fighter pilot with 43 bomber kills, provided particularly revealing testimony. "The American bombers have changed. Our standard attack patterns no longer work. We can damage their wings severely, but they will not break. It is troubling." German intelligence correctly identified wooden wing modifications, but dismissed them as desperate improvisation rather than technological advancement. This intelligence failure would cost the Luftwaffe dearly, as American bomber formations became increasingly difficult to destroy. The statistical impact was overwhelming. Bomber loss rates dropped from 25% per mission to 7% per mission within 2 months of wooden wing implementation. More importantly, crew survival rates increased dramatically because aircraft with wooden wings could absorb battle damage and still reach friendly territory. Captain Sullivan, now promoted to major and commanding a wooden wing-equipped squadron, summarized the transformation. 6 months ago, completing a tour of duty was essentially impossible. Now our crews have a realistic chance of going home. Harold Zimmerman didn't just improve aircraft design, he saved thousands of lives. The success created unexpected problems. Aircraft manufacturers demanded access to Harold's technical specifications for post-war commercial applications. The War Department classified Harold's designs as military secrets, creating legal battles that would continue for decades. Harold himself remained focused on immediate problems. "We've solved the bomber wing issue," he told Dr. Chen during a rare quiet moment at Wright Field. "Well, but there are other aircraft, other structural problems. This is just the beginning." By December 1943, Harold's wooden wing modifications had been installed on over 800 aircraft across multiple theaters. The quiet Carpenter from Minnesota had revolutionized military aviation and fundamentally changed the strategic bombing campaign's effectiveness. But the greatest validation came from the crews themselves, men who flew dangerous missions with confidence that their aircraft could bring them home despite enemy action. Harold Zimmerman never lived to see the full impact of his innovation. He died in a car accident in Minnesota in 1947, just 38 years old, while returning from a lecture at Boeing where he'd been consulting on post-war aircraft design. His obituary in the Minneapolis Tribune was 3 paragraphs long and didn't mention wooden wings. But Harold's legacy lived on in ways he never could have imagined. His laminated wood construction principles became the foundation for composite materials that would revolutionize aerospace engineering. The carbon fiber wings on modern aircraft trace their conceptual origins directly to Harold's garage experiments in 1943. Dr. Sarah Chen, Harold's adhesive chemistry collaborator, went on to develop the synthetic resins that enabled the space program. The heat shields that protected Apollo capsules during re-entry used advanced versions of the same bonding technology she'd created for Harold's wooden wings. Major Patricia Williams, who had supervised Harold's military testing, became the first female chief engineer at Lockheed after the war. Her advocacy for damage-tolerant design principles influenced every major aircraft development program for the next 3 decades. The wooden wing program itself was classified for 30 years. When documents were finally declassified in 1973, aviation historians realized they had missed one of World War II's most significant technological breakthroughs. Harold's innovation had saved an estimated 2,400 aircraft and 21,600 aircrew lives during the last 18 months of the European War. Modern aircraft manufacturers rediscovered Harold's damage tolerance concepts during the 1970s, when metal fatigue problems plagued early jet aircraft. Boeing's 777, introduced in 1995, incorporated laminated wing construction principles that Harold had pioneered 50 years earlier. The connection to contemporary aerospace technology became clear during the development of unmanned aerial vehicles. Drone manufacturers found that Harold's flexible wing designs provided superior performance characteristics for aircraft operating in hostile environments where battle damage was expected rather than exceptional. Perhaps the most fitting tribute came from an unexpected source. In 2010, the Experimental Aircraft Association inducted Harold Zimmerman into their Hall of Fame with a citation that read, "For demonstrating that innovation comes from understanding materials, not from formal credentials, and for proving that impossible problems sometimes have simple solutions." Harold's wooden briefcase, the same one he'd carried to Wright-Patterson in 1943, resides in the Smithsonian's National Air and Space Museum. Displayed alongside it is a fragment of laminated Sitka spruce from one of his original wing modifications, recovered from a B-17 that crash-landed in France in 1944. The crew survived because Harold's wing had absorbed enough battle damage to destroy 3 conventional aircraft while still maintaining structural integrity. The placard beside the display tells visitors that this piece of wood represents more than technological innovation. It represents lives saved by one man's refusal to accept that problems were unsolvable simply because experts said they were unsolvable. Today, when aerospace engineers face seemingly impossible challenges, some still ask themselves a question that has become legendary in the industry. What would Harold do? The answer usually involves looking at familiar problems from completely unfamiliar directions and refusing to be limited by conventional wisdom. Harold Zimmerman proved that the most revolutionary breakthroughs often come from the most unexpected sources. His wooden wings didn't just change aircraft design, they changed how engineers think about solving impossible problems. In a world where complexity is often mistaken for sophistication, Harold's simple, elegant solution reminds us that sometimes the best answers are hidden in plain sight, waiting for someone brave enough to try something everyone else knows won't work.